So welcome to another edition of the Finite Element Seminar at LLNL. It's our pleasure today to have Dr. Gonzalo de Diego from the Courant Institute. Gonzalo is originally from Spain, did his PhD in Oxford with Patrick and and he's visiting the lab today. So if you want to meet with him, please let me and Cosmin know. He's a visitor of Cosmin. And he's going to talk about numerical solvers for problems in glaciology. Interesting topic. So Gonzalo, thanks for coming, and please take it away.
Thank you very much, Stano. And thank you everybody for being here virtually and in person. Essentially, my topic of today is viscous contact problems in glaciology. I'm aware that probably a lot of people haven't worked with glacier modeling, so I'll try to make that clear. But before I talk about glaciers, I just wanted to say that this topic is essentially the focus of my PhD thesis, which I finished in September at the University of Oxford under the supervision of Ian Hewitt and Patrick Farrell. Perhaps Patrick Farrell is a name that's familiar to several of you. And I started a postdoc at the Courant Institute under the supervision of Georg Stadler. And the focus of my postdoc is no longer ice sheets, it's sea ice. So ice seems to be my topic, but sea ice and ice sheets are very, very, very different physical processes. Anyways, today I'll talk about ice sheets. So before I step into these contact problems that I want to talk about, I just want to motivate the mathematical modeling of ice sheets, why it's important. And really, we care about ice sheets because they're a fundamental element of the climate system. In particular, as I write here, the ice sheets of Antarctica and Greenland hold a mass of ice that, if it were to melt, sea levels would rise by 65 meters. So as you can imagine, not just for the sea level rise, but for the energetic role that these massive amounts of ice have in the climate system, we're very interested in understanding how they evolve. In particular, understanding how ice sheets evolve not only implies understanding how they melt, but also how they flow. And as you see in this photograph to the right, which is a photograph of Elephant Foot Glacier in northeast Greenland, you can see the ice sheet flowing towards the ocean, and it really looks like a kind of like bubble of honey, right? So this is a very good representation of ice sheet dynamics and the fact that ice actually flows when viewed over sufficiently long time scales. So this will be fundamental to understand the mathematical systems we'll be working with. On top of that, we're also interested in understanding how ice slides over the bedrock. This is a topic that will come up again soon. And also how meltwater, say on the surface of the ice sheet, percolates into the base of the ice and also affects these dynamics. In particular, there's a very interesting interplay between meltwater and sliding that is fundamental to understand ice sheets and their evolution. I'll be focusing on a very particular set of problems that we've come to call viscous contact problems. So these are time-dependent viscous flow problems where you have a fluid in touch with a solid surface and you allow for the possibility of detachment and reattachment. And below, I show the two main examples that arise in glaciology, which were the focus of my PhD thesis. And those are, on the one hand, marine ice sheets. Marine ice sheets are big masses of ice sheets that slide from the continent into the ocean. And at a certain point, they go afloat, as you see here. So a detachment occurs at a certain point due to the buoyancy of ice, which is lighter than water. This point is called the grounding line, and it's difficult to stress just how important understanding grounding line dynamics is. You know, you go into like the intergovernmental panel of climate change, and you will see citations of actual technical papers on grounding line dynamics. People talk a lot about this possibility of a marine ice sheet instability that will create a discharge of ice that starts accelerating in time under certain dynamic conditions. On the other hand, there's a much more niche problem called subglacial cavitation, which I'll talk about now. And in fact, even though I just insisted on how important marine ice sheets are, for the purpose of mathematical modeling, I've come to enjoy talking about subglacial cavitation much more. It's a very nice toy problem, and the maths become interesting. So for the purpose of illustrating what a viscous contact problem is, I'll be talking about subglacial cavitation. And to make clear what subglacial cavitation is about, it's essentially a process that occurs at the interface between the ice sheets and the bedrock. So if we zoom in to this interface between the ice and the bedrock, you can imagine that the bedrock is actually very bumpy, right? And along these bumps, the ice is flowing, and due to the effect of flowing and high water pressures of water from usually meltwater from the surface of the ice that comes down to the base, these cavities form. And these cavities are important for two reasons. First of all, since the 1960s, they're seen as really one of the fundamental mechanisms in understanding the relationship between sliding velocities, what I call UB here, and sliding friction, what I call tau B. But on top of that, the fact that these are water-filled cavities and the water pressure of these cavities are important for determining their geometry, we essentially establish a link between, on the one hand, the hydrology system under the glacier, what I said before of this meltwater that percolates to the base, and the dynamics of the glacier. Because as we will see later, this water pressure actually affects how the glacier slides over the bedrock. So this is a kind of toy problem I'll be talking about now for the kind of mathematical and numerical modeling. But I'll just quickly show another motivation of why we care about this. So as I just said, this is all about developing numerical schemes for this problem. And the origin of this project back 4 or 5 years ago, was the fact that these kind of viscous contact problems have only been solved until now with a finite element module called Elmer Ice. Maybe some of you are aware of it. And in particular, one of the papers where they solved this subglacial cavity problem, in fact, the only one that we knew about. And you look at the numerical results, so I include a plot of this paper to the right. You have, on the one hand, the geometry of the cavities, so that's the top panel. And under it, you have these plots that represent the normal stress exerted by the ice against the bedrock. And if you look at these, you see that you have a lot of strange artificial numerical oscillations. So this seems to be inherent to the numerical results obtained with Elmer ice. And as I write here on the left, that was really one of the main motivations for starting to look at this problem, the fact that existing results appear inaccurate and unstable. And on top of that, this problem has a very interesting mathematical structure. As you will see now, it essentially involves a variational inequality, and that opens up a lot of options for solving this problem in different ways. And in this existing literature, we realize that none of this mathematical structure was acknowledged. So this is essentially, I'm just trying to explain why we started working on this problem. And in a few slides toward the end, I'll show another figure that we obtained, and you'll see that we obtained much cleaner results. So I'll come back to this. But before I do that, I'll present the mathematical model we're looking at. So on the right, you see an idealized representation of the problem we want to solve, this subglacial cavity problem. What matters here is that the domain we'll be solving the PDEs on is omega, which is in white here to the right. That's essentially the boundary layer of ice in between all of the ice sheets on top and the bedrock below. The geometry of the subglacial cavity of the bottom boundary of omega is given by h. And in particular, what's very important for us is to realize that it's evolving in time, but we have a subset of the boundary, of the lower boundary, here marked in red, gamma A, which is where the ice is attached with the bedrock, okay? Now, In order to determine the evolution of this cavity, on the one hand, we have to know how the ice flows, and we use Stokes equations for that, since we consider it a viscous flow. You see that there's a nonlinearity here. That has to do with the fact that glaciologists like to work with a power law rheology, or the viscosity, so you get a kind of like P Stokes, or in this case, R Stokes structure. But what matters for us here is the fact that we're working with these contact boundary conditions that you see here. So it's these three boundary conditions. What they tell us is the following. The first condition, which is the kinematic condition, essentially says that the ice cannot penetrate into the bedrock. The velocity has to go outwards. That's why the normal component has to be negative, because it's an outwards pointing normal. The second condition, what it essentially tells us is that the ice can press against the bedrock, but cannot pull from the bedrock, right? That's very reasonable. And finally, the third condition, this one here, says that either the ice detaches and U dot N is non-zero, or the ice presses against the bedrock, but you cannot have both at the same time. This is a complementarity condition. So those are the contact boundary conditions. And then on top of that, what makes this problem special, because perhaps many of you already recognize this kind of structure from elasticity. It arises in elasticity, a very similar problem. What makes this problem different is the fact that it's a viscous problem. So we also need a free boundary equation to evolve the geometry in time. It's not like elasticity, where once you solve the linear elasticity equations, you already get the deformed configuration. No, here we have to have a coupling between the free boundary equation and the Stokes equations. And the free boundary equation essentially tells us how the cavity geometry, determined by H, the cavity roof, evolves in time in terms of the normal velocity U dot N. So a very interesting fact that arises here is that when we discretize this problem, the way we treat U dot N in the free boundary equation and the way we treat U dot N in the contact boundary conditions are kind of coupled in a special way that I will make clear. But these are the equations we are solving, basically. So just to make the numerics a bit clear, we're considering a very simple scheme where we decouple the Stokes equations and the free boundary equation. And essentially, we're iterating in time. And at each time step, we solve the Stokes equation, we get a velocity field, we evolve the boundary, we deform the domain, and then we return to the Stokes equation. So the main takeaway here is that we are solving the Stokes equations and the free boundary equations in this decoupled manner. So the basic questions that arise here is, and this is what the next slides are about, how do we solve the Stokes equations with contact boundary conditions? There's many ways to do it, but what makes this problem unique is the fact that then we have to couple it with a free boundary equation. And this coupling is essentially something I'll try to be as clear about as possible. Okay, so let's talk about the Stokes equations with contact boundary conditions. Anyone who's worked with these contact boundary conditions knows that the moment we formulate a weak formulation of the problem, which is what we want to work with since we're going to solve this with finite elements, we don't get a variational equality, but we essentially get a variational inequality. So if you look at this weak formulation, what's important to notice here is that we seek the velocity in K, which is not a vector space. K is a convex subset of a vector space, where essentially we enforce what corresponds with the kinematic contact condition, the no penetration condition. Okay? And, next slide, sorry. I feel like whenever I touch this, I go to the next slide, but we have a variational inequality, but it's more interesting to view this as a minimization problem, right? So this is essentially minimization problem where we have two constraints. On the one hand, we want mass conservation, the divergence-free constraint, which many of you probably work with the Stokes equations. And we also want the contact constraint, right? So these are two constraints. And the main point here is that on the one hand, we have to choose, when discretizing this with finite elements, a finite element space for the velocity and the pressure. That's very well understood. But what will make this more interesting is the fact that the inequality constraint, so the kinematic contact condition, can be enforced in very different ways at the discrete level. So this is something we'll play with now. But just before I go there, just to make things clear, I just want to say that I'm solving all of this in Bedrock, which is a finite element module in Python, pretty much an inheritor of the kind of Phoenix philosophy. And for the velocity and the pressure, I'm not going to make my life complicated. I'm just going to take Taylor-Hood. So that's piecewise continuous quadratic polynomials for the velocity and continuous piecewise linear polynomials for the pressure. Much more interesting than this is the fact that in order to represent all the different possibilities for enforcing this inequality constraint, I'm going to introduce a discrete normal trace operator. So this is essentially a discrete representation of the normal component. Why am I making my life so complicated? Well, to make things clearer, this inequality constraint at the discrete level, once we're working with a mesh, can be enforced in many different ways. The most natural way is, as you see here to the left, I simply enforce this constraint on every point of the contact subset of the boundary. However, I can also weaken this. And I can say, well, instead of enforcing this inequality constraint at every point of the red boundary, gamma A, I could also simply enforce it at the midpoints of each edge, as you see here. I can also enforce it in a kind of average-wise way, right? So there's many different ways in which we can enforce this. And again, why am I making my life so complicated?
Can I ask a quick question?
Yeah, please.
When you say in all points, do you mean the degrees of freedom? All degrees of freedom, or do you actually mean enough?
Well, it goes hand in hand. So the velocity lives in a space of piecewise quadratic polynomials. So to enforce it on every point, basically on every edge, I'd have to enforce it at 3 different points, right?
That's not to, if it's positive in those points, it's not to be positive anyway.
Well, that's a good point.
It's not always the case for the data. You can get quadratic polynomial that's positive in the point. And it. So you mean in the all point?
I mean at all points. Yeah. So I'll show later. Like, so this is the next slide. So the most kind of obvious way to solve this would be to simply enforce it on every point, and we can enforce this with a penalty method by adding the right penalty. And this would be like the most natural way to do it. But the crazy thing is that you have to evolve it with a free boundary, right? So that means that we have to solve it, say, hundreds or thousands of time steps. And when doing it in this kind of naive, straightforward way, it actually becomes very inaccurate. And this is a problem that I still haven't come to understand very well, but I think it's related to the fact that perhaps with quadratic polynomials, enforcing it on every point perhaps creates some complication because it's unclear how that is resolved at the level of degrees of freedom, maybe. It's something I don't understand very well, but in this case, and one choice would be to enforce it on every point. But it's a good point. Yeah, you can also just reduce it to the degrees of freedom. I've also tried that and it doesn't work very well though. So this is where the problem becomes interesting, that we can enforce this inequality constraint in many ways, and the kind of obvious ways to solve it don't work that well always. So as I said before, here we had these 3 possibilities. So now I'm going to focus on this 3rd possibility, on average-wise enforcement on edges. And if we do this, we essentially solve this minimization problem where our constraint becomes this kind of average-wise statement of the inequality constraint. And one very nice way to solve this, at least in Bedrock, it becomes very easy to implement, is by enforcing a Lagrange multiplier. So if we look at the first-order optimality conditions of this minimization problem in terms of a Lagrange multiplier that enforces this inequality constraint, we essentially get this system where you can see on the one hand that the Stokes equations are now a variational equality. So the first 2 lines, where we have an additional term that enforces the inequality constraint. So you have an additional kind of forcing term involving the Lagrange multiplier lambda h. The Lagrange multiplier lambda h, as you can see at the first line, lives in a piecewise constant space of polynomials along the boundary. This is a natural consequence of enforcing an edgewise average statement of the inequality constraint. And what's very nice is that you essentially get an average-wise statement of the contact conditions, as you see down there. So this is essentially analogous to those 3 contact conditions that I showed at the beginning, but now it's stated in this kind of edgewise average way, where each E is an edge of the mesh, right? And this you can easily rewrite in terms of this max operator as a nonlinear condition. So this is what we implement directly in FireDrake, simple to implement. And it kind of shows how you can go from contact conditions, which are these set of inequalities, to a nonlinear equation, right? So now we have an equation, and this is what we implement in FireDrake. Okay, so until now, it's all about the discrete Stokes equations. But as I said, one very important aspect of this problem is that we're constantly coupling with a free boundary equation. So how does this coupling work? So the free boundary equation is essentially at the continuous level, what you see up here. And I'm just going to choose a very simple discretization. So finite differences forward Euler. So you get what you see below. And here, the interesting thing is that, again, we have to introduce a normal velocity component. And what turns out to be fundamental to get an accurate algorithm for these viscous contact problems is what I call, on the one hand, a notion of compatibility. So the choice I make for the representation of this normal trace operator actually has to be compatible with the choice I made before for the way I discretize the inequality constraint. So remember, it was average-wise. And on top of that, this free boundary equation in the context of this subglacial cavity problem is actually an advection problem, in the sense that we're advecting the cavity roof in the direction of the flow. So we also have to take into account the fact that we need to stabilize this problem. So these are the 2 constraints that we have to take into account when constructing the discrete free boundary equation. And how do we do that? Well, it's kind of obvious, right? On the one hand, we use the average-wise velocity on each edge. Why do we want to do that? Because for this average-wise velocity, we're satisfying the contact conditions exactly. So we have a clear distinction of regions that want to detach and regions that want to stay attached, because we're solving those contact conditions up to machine precision with a Lagrange multiplier. But what makes it more interesting is the fact that if you look at the notation I take here on the right panel, the edge EI is immediately downstream of the node HI. So, sorry, I touched the screen and something happened. Yeah. Actually, anyway, so if you take a look at my notation, the discrete free boundary is solved for each node HI. And if you look to the right, the edge EI, from which I choose the velocity, is located immediately upstream, because I'm assuming that the flow goes from left to right of the node. So this is essentially a form of upwinding. So this is kind of our solution to this issue of, on the one hand, enforcing the contact conditions at the level of the discrete free boundary by choosing this average-wise velocity, and on the other hand, stabilizing by choosing the velocity associated to the edge immediately upstream. So yeah, so this was our way of solving the problem of coupling the free boundary and the Stokes equations. And now I'll convince you that it works well by showing you a video, which I have to change window. Actually, you need to go a few more. Oh, sorry. I feel like we already knew how to do this, and now it's not working that well. Oh, thank you. So, yeah, there was a little issue with the presentation, and the video wouldn't come up, so I just opened it. So in this video, on the one hand, you have a cavity at the right panel. So now the cavity is attached, so you don't distinguish the cavity from the bedrock. And what you see below, unfortunately, the legend is associated with the PowerPoint, so I don't have it here. In black, you have the normal velocity. So this is at time 0, I still haven't played it. So this is where the ice wants to detach. And in red, you have the Lagrange multiplier that represents the force exerted by the ice against the bedrock. So here you can already see that at t = 0, we have a perfect distinction of regions that want to detach and regions that want to stay attached. And as you see, as I play this over time, you see that this changes. So actually, it's a very crazy problem because we have singularity at the reattachment point. It's that peak that you see there with the Lagrange multiplier. And anyways, with the video, I won't show it again. It's a bit complicated. Or maybe now I just have to do this, right?
Actually have
VLC. Oh, it's there, but it doesn't matter. It doesn't matter very much.
Sorry about that.
Don't worry.
We'll find. We can find it.
This is just a classical issue of compatibility with PowerPoint and Windows Mac. Anyway, that was just a video to show what these simulations look like. And if we return to that image that I showed before where I compared with Elmer ice, you can see that the steady states we find, here what you have is sigma NN, which is essentially the force exerted by the ice against the bedrock, and it has to be negative. And when you're solving it in this neat way with the Lagrange multipliers, you're exactly enforcing the contact conditions at every point. So it's very nice to see that these numerical results essentially show that we don't get those wiggles anymore, and also that minus sigma NN is strictly positive, or, well, it's non-zero, non-negative, sorry. So essentially this means that the contact conditions are enforced exactly. And that turns out to be very important for a robust and accurate computation. Okay, so I'm going to return to this idea of the subglacial cavities being fundamental for glacier sliding by showing you an application of this algorithm where I'm going to compute what people in glaciology call a friction law. So a friction law is this relationship F between, on the one hand, the sliding velocity UB is the velocity at which the glacier slides over the bedrock, and tau B, which is the friction exerted by the bedrock on the glacier. And oftentimes you have additional parameters involved in this friction law. So in particular for subglacial cavitation, if you do a kind of non-dimensional analysis of the problem, you realize that the other factor that's important here is what people call the effective pressure. So what is the effective pressure? The effective pressure is a difference between an overburdened ice pressure, which represents the weight of the ice sheet on top of the cavity, and the water pressure, which is the pressure exerted by the water inside the cavity upwards, right? So it's this difference, this effective pressure, that turns out to be a fundamental variable in subglacial cavitation. And we can find the form of F essentially by choosing different pairs of sliding velocities, which is an upper boundary condition, as you see here, and effective pressures, computing steady states of the cavities, and then finding tau B by integrating the pressure exerted, the stress exerted by the ice sheet against the bedrock in the horizontal direction. If we integrate that, we find the friction. So if we do this for many steady states, we get something like this. So each dot here is a steady state. The left panel, the vertical axis is a non-dimensionalized form of the stress. It turns out to be a good way to non-dimensionalize it in this way. The lower panel shows a sliding velocity to a particular power that has to do with the power law exponent of the viscosity, again divided by the effective pressure. And as I said, each of these points is a steady state for this subglacial cavity system. So we have a geometry, and it turns out that along the initial segment to the left, which clearly has a kind of linear looking, but it's a power law form, what we have is that the ice stays attached to the bedrock. And it's only when you reach a critical velocity or effective pressure that you start having detachment. You get to maximum, which actually represents the inflection point of the sinusoid bedrock, where you have the maximum friction, and then you start having what they call this rate weakening regime, where an increase in velocity or pressure, water pressure, involves a decrease in friction, and you see that the ice detaches more and more as you advance. So something you all probably notice is that we start getting, again, these kind of wiggles. This has to do with the fact that you need an incredible amount of refinement near the contact point, because the singularity that you saw before in red of the stresses becomes more and more dramatic. So you have to refine like crazy, essentially, because a small change in the contact point involves a large change in tau b in these regimes. But yeah, this is essentially the numerical results for the subglacial cavitation problem. And now, for the last 3-4 minutes, I'll just talk about the other topic. I only have 2 slides, but as I said before, marine ice sheets are a very important problem. This is an example of what the profile of the marine ice sheet of the Antarctic ice sheet looks like. So essentially, if you were to cut here in Antarctica from point B to B prime, so this is what they call the West Antarctic ice sheet, you would get this profile that you see here, where you have 2 big ice shelves, which are floating ice sheets. So one is a Rhone ice shelf here, which corresponds to this area, and the other is a Ross ice shelf. If you look at this panel on the left, the color represents the ice velocity. And you can see that the ice flows incredibly fast in those regions. So these are regions of fast-flowing ice from the continent into the ice shelf, into the ocean. This is what causes sea level rise, essentially, right? Because grounded ice does not contribute to sea level. But as soon as it starts floating, it does contribute to sea level. And as I said before, there's a lot of interesting dynamic processes here. On the one hand, these ice shelves serve as buttressing that keep the ice on the continent. Yet sometimes they collapse. There's suddenly like a dramatic sudden breakage of a large chunk of ice, and that changes a kind of force balance and creates more flow. So these are very important components of the climate system. And we've been studying these systems by solving what we call this parallel slab marine ice sheet, where we just consider an idealized situation where ice slides from this inclined slope and it goes into the ocean. And what you see here is essentially what the steady states look like. At a certain point, they detach, and then the ice starts thinning as it flows into the ocean. And something that we looked at with our solver were flux thickness relationships. So that is, if I find a steady state, then at the grounding line, I have an ice thickness, I have an ice velocity, and this relationship between flux and thickness is very, very important because it tells us a lot of information about how a change in the grounding line configuration changes the amount of flux into the ocean, which is essentially what matters for sea level rise. Also from a mathematical modeling point of view, with these flux thickness relationships, you can actually solve a simplified free boundary problem. This kind of acts like what they call a Stefan condition in these free boundary problems. So very interesting system. And as I said, I don't want to show too much, but we've basically been studying what these grounding line flux functions look like for different regimes. Sometimes the ice is dominated by sliding, so there's hardly any shearing, but other times the ice is stuck on the bedrock and you get more of a shear dominated flow, as you see here. And you can already see here that the geometries change dramatically. So it's very interesting to see how these flux thickness functions also change. And yeah, that's basically one of our projects that should be out soon, but I won't talk too much about that, and I'll close the presentation now. I realize that maybe I was a bit faster than I expected, but yeah. So the conclusions are that in order to compute these viscous contact problems accurately at the numerical level, what we did was enforce this discrete piecewise constant contact boundary condition and use that formulation of the contact conditions for solving the free boundary equation. So essentially, there's this kind of coupling between how you solve the contact conditions and how you evolve the boundary. And one aspect of this problem, which I didn't really talk about, but essentially we find steady states by solving the system in time. So we allow it to advance from an initial state into a steady state. And this is very time consuming, and at times it's really not robust. So I think one of the future improvements will be to figure out a way of coupling this variational inequality and free boundary equation at the numerical level. That is, find a way of posing a nonlinear problem where our unknowns are the flow solutions, right? The velocity and the pressure, perhaps the Lagrange multiplier, but on top of that, the free boundary. So I think this will require ideas perhaps from
friction.
how do they call it? Shape optimization, right? We'll have to evolve the geometry of the problem as well. It'll be one of the additional unknowns. But this will allow us to do more stable time-stepping schemes, perhaps by doing implicit Euler instead of forward Euler. But on top of that, for finding steady states, perhaps we can find steady states directly with Newton's method, right? Solving for the geometry and the flow solutions.
But anyway,
That's all. Thank you very much for your attention.
Thank you, Gonzalo. Okay, so questions. If you're online, feel free to unmute and just ask.
Well, I guess, you know, I think the way I understand it, your issues with the contact where if you try to enforce it, if you tried to enforce it basically on a nodal basis and you found that that was unstable.
Mm-hmm.
And but that I guess it's that you would actually have an issue if you try to enforce it kind of on your edge average basis. That could also produce an instability because you kind of don't have the same number of constraints as you have degrees of freedom. So I guess, do you have an insight as to why you had an instability when you tried to enforce it nodally?
Yeah. So first of all, what you set up this mismatch between degrees of freedom, I think that's okay because what you have here is essentially a stability condition, an instable condition, and we can prove that that condition does hold between the quadratic polynomials for the velocity and the piecewise constant polynomials for the normal component. So I think in that sense it's stable. The issue regarding the quadratic polynomials and the direct enforcement of the contact conditions, you know, it has to do with the fact that, let me see what the best way to show this is. So here, you can see that I have in black a normal velocity. This is at time t equals 0. And essentially, what I get when I use quadratic polynomials is that, I always use quadratic polynomials. If I enforce the inequality constraint directly in this kind of pointwise sense, is that, on the one hand, the contact conditions are exactly solved. I don't get negative velocities. But usually, near the edge, you see that some points kind of wiggle upwards a little bit. It's almost like I don't get this clean u dot n that I do get with edgewise averaged enforcement. And those little wiggles, if I were to just solve this problem once, perhaps it's okay. But when evolving the free boundary over time, hundreds of time steps, they end up destroying the solution. That's not that much insight. I think I'm not too sure of why those wiggles occur.
Okay, thanks. You're around today though, right?
I'm around, yeah.
Okay. Thank you.
Thank you.
So maybe to follow up on this, one thing you mentioned was resolution. These simulations, do they use stuff to measure final?
No, they don't. They don't, because I don't have it in Firedrake, basically.
Okay. But if
I had it, I would use it.
them, or do you think it will help with some of the
I think so. Yeah, for sure. For sure.
Right, other questions?
I have a question. You said you were using forward Euler. Was that for so was it explicit or was it implicit?
Explicit, because I have to decouple the free boundary equation with the Stokes. Yeah.
Well, I mean, you could obviously write it monolithically, or there's even staggered approaches with implicit that you could use that are stable, like, you know, people use in porous flow, right?
I could. I think the issue is that as soon as something becomes implicit, I have to figure out a way of solving the Stokes equation and the free boundary together in a coupled way. And
There's like these fixed stress, or like these methods by like Mary Wheeler called the constant stress, and other ones by Zankovich, that they've been doing this stuff, because this just looks like BO kind of type of problem, right? You have like a Darcy flow, when you have an effective stress with the the grains between the in the soil. I would think that would be something you could apply here, right? Because you got the same kind of issues.
but do you mean that there's also a variational inequality?
Well, you can so like there's variational inequality that shouldn't cause any issues other than you have to solve the variational inequality. But as far as the coupling is concerned in the time integration scheme, I think it should stay stable. Like that. So what? Maybe some of the people you should talk to here are the people that are working on tracking, right? Because there's a lot of similarities here. Geos is one of the codes we have here at the lab that do Reynolds lubrication between the cracks, and they have the variational inequality, but they also have the rock that's sitting above it. So it's, in your case, you have ice. You have a different friction law perhaps, but maybe we should put you in touch with some of those folks, because they have the same issues. They use the piecewise constant pressures, and then they also use but they're using linear elements, and they have to put stabilization in there. But yeah, but it was interesting. Thanks.
Oh, thank you very much. Yeah, that would be very interesting too.
The last question is that when you were solving for the pressures for the quadratics, and you were using all the nodes, were you doing it with collocation, or were you doing it with intervals along the trace space? Were you using like piecewise or polynomials, quadratic polynomials for the pressure, or were you just doing everything with collocation?
So when you mean the pressure, do you mean the Lagrange multiplier, lambda?
Yeah. The Lagrange multiplier. You have a space for the Lagrange multiplier, right? So you could use quadratics, or you could use piecewise linear, or in your case, you use piecewise constant.
Yeah,
Piecewise, which is in fact stable, but it's not as accurate. But for this, it probably, I don't know, might be suitable, but
I think it's suitable for this. I mean, the accuracy I want is
well, it's nice.
it's already constrained by this very simple discretization of the discrete free boundary, which at the end of the day, the discrete free boundary equation really is what matters here, since I'm interested in the geometry of the subglacial cavity.
Yeah. No, I understand. It works nice with the upwinding too.
Yeah, exactly. Yeah.
No. Nice.
Thanks, Mike. Phil, did you get one?
Nice. Yeah, actually, can you go back to the static 16 spread for this?
Yeah.
So are you to solve this system, or are you using like a semi-smooth
Semi-smooth Newton. Yeah. Yeah, it works very well. And Fardrick just does it automatically. I don't even have to do anything. Just tell Newton and it takes care of it.
Okay. Nice.
Yeah, I see a comment from Jerome that with quadratic volts to the partial pressure stable. Any other questions or comments?
Nice.
So Fire-Drake does the semi-smooth Newton automatically, even with the friction?
Yeah, it does.
Nice.
With the maximum operator that you see there, I just literally write that with the UFL language and plug it into Newton, and it takes care of it very well.
Nice.
I think you didn't mention is how big this simulation? What's the resolution here?
The resolution for the computations I showed, probably I solve Stokes equations with just 10,000 mesh cells. But I think what makes it annoying is that, especially for these highly detached states, because I use explicit Euler, I have to do small time steps. So maybe I solve it 1,000 times when evolving in time. So I think that's where you start getting the kind of like computational issues.
And this is all serial.
Yeah. Oh yeah. It's a very, very rough implementation, to be honest. And I think if this is a problem that people want to explore in more complex situations, for example, extensions to 3D, then there is a lot that has to be done and should be explored.
I don't see the actual friction in the equations. You said you were applying friction, but you just show a normal pressure. Where's the friction in the...
Oh yeah, sorry. I think I misunderstood you by friction there. I get confused with friction in a different sense. No, there is no friction here. There's slip conditions between the ice and the bedrock of the tangential direction.
But you did have friction in the model, right? You showed some results or you showed a friction model.
Yeah, but I think conceptually it's fundamentally different. It's more that...
Okay, I get it. Yeah, it's just a drag that comes from the bumps and stuff.
Exactly. It's by solving this frictionless system many times that you find a friction law.
Yeah,
ironic.
From the aspersions, basically. Yeah.
Nice.
Okay, more questions?
Nice.
I have one question. Yeah, so in some macro scale, larger scale point of view, so that cavitation and a kind of relative sliding, whether that is viscous or viscoelastic interaction, but have you ever considered a kind of multiple relaxation kind of dynamics? So local region 1 and local region 2 somehow differentially sliding, differentially posed, differentially emerging different viscous, two viscosity, simply said. Nice. Region domain 1 and domain 2. Yeah. With, nice. For example, with different temperature gradient, and for example, I don't know what's the main mechanism of that generation of cavitation, cavity, and that propagation, but a kind of volumetric expansion and contraction might be one possibility, and temperature gradient, but whatever that is, heterogeneous, non-uniform viscosity. Have you ever thought of that?
So I think you're asking if, when I come to the Stokes model that you see here, nice. I saw it including more complex viscosities that perhaps couple with temperature, but also with possible elastic effects. Is that what you were asking me?
Yeah. And also in micro scale, so kind of a grain boundary, but whatever that is, some kind of polycrystal, but still in large scale dynamics and modeling, a kind of multiple relaxation time constant. That's I'm actually asking, but kind of not only homogenized one viscous relaxation, but there might be multiple time constants.
Yeah, I see what you mean. Like, on the one hand, there's elastic effects, which have a characteristic time which is much smaller than viscous effects, for example.
Mm-hmm.
Nice. Obviously, this is a very simplified problem. But what's very interesting is that there's actually laboratory experiments of these subglacial cavitation problems. There's some folks up in Wisconsin that have created a machine that actually moves the ice over several days and creates these cavities, and they look very similar, but we did some comparisons and there are some differences. And one of the reasons we think that we don't have have this misfit is possibly due to elastic effects. So ice is viscous when evolving over, say, 10 days or more. I think that's what they call the Maxwell time of the kind of viscoelastic system. But these steady states in the kind of regime that we consider, which is like bumps of around a meter and velocities of, say, perhaps 100 meters per year, which is representative of mountain glaciers. In those time scales, you do have viscoelastic effects. And in theory, it should be considered, but I've kept it very simple. But I think if you were to do a proper analysis of this problem, you would have to consider more complex viscous models that include these kind of elasticity effects and also temperature effects. I'm not sure if that answers your question. I think I... Nice.
Thank you very much.
Stand up. You're welcome. Nice.
Right. Elias, do you want to unmute and ask the question you posted in the chat?
Sure, if you can hear me all right.
Yeah.
So basically on the friction topic again, I was wondering if you were to include actual friction between the bedrock and the ice, is that significant compared to the friction that you get from just the slipping across the geometry?
Yeah, that's a good question. So essentially the friction we're computing here is what you would call form drag, because it's essentially drag just caused by the form of the bump. But yeah, at the end of the day, friction is caused by many different spatial scales. So we could zoom even more and we'd have a whole other range of mechanisms occurring at smaller time scales. And some people have tried to add that by, say, including Coulomb friction, for example. It doesn't change the form of the drag too much, to be honest. But with a system like this with glaciers, so much is happening that at the end of the day, people just prefer to work with more simplified systems that can actually create a conceptual framework that can help you understand certain phenomena. So yeah, you could complicate it much more, but it's always going to be far from reality in a way, right? So I guess it's...
Yeah, makes sense. I was just wondering if it was significant or not.
I think the kind of agreement is that it's not too significant.
Okay, I see.
Modeling wise, it's simple to include. Yeah, you would just have an additional nonlinearity in this system here. Nice.
Yeah, thank you.
You're welcome. Nice.
You mentioned briefly 3D. So, I think you can imagine, first of all, the glaciers are 3D. I can imagine this becoming much more complicated.
Yeah.
Which portion of it do you think will stay the same and which portion will get to be outdated?
I mean, I think that what really requires some new thinking is this step. How do you devise the discretization of the free boundary?
Do you think this integral average approximation for U.N is going to be happening with it?
Maybe not.
I mean, even not 3D, but like, I mean, now in 3D, if you have quads instead of x's, so if you have deltas instead of, which you really want to have in this simulation, and so this spaces are not flat anymore.
It's a good point. I think all of that would require a lot of new testing and thinking, which I haven't done. But I think it would be fundamentally different, yeah.
Well, could you come up with an homogenization for the aspersions? Because people do that, and that could motivate basically a frictional law. You say this is form drag, and it is, but you could come up with you showed something that looked like a friction law, and that I would think in 3D that's probably what you would eventually use, wouldn't you? Because you just couldn't afford to model the aspersions individually. Is that what people do in practice? Do they? I mean, because obviously this is good, and this is motivating, and it shows you a lot of the different, a lot of the physics that go on underneath. But wouldn't you eventually just kind of want to come up with just a type of friction law that's a complicated friction law, but then you don't have to model the aspersions?
Yeah, exactly. No, people work with a lot of friction laws, and there's a lot of research into this topic, also from more analytical methods. And the general consensus is that what matters is a kind of power law.
Right.
So the weakening that you get here, you wouldn't get that in nature because bumps are more complicated. And it's all about having a dominating slope. So if you have a lot of bumps of, say, imagine a superposition of several waves over this one, essentially what would happen is that there's always going to be a dominating wave such that you don't get into this critical rate weakening state and you get something like a power law.
Sure. And people do this in tribology, traditionally not necessarily with ice glaciers, but they come up with these complicated friction laws that are history dependent too. And sometimes they even use like multi-scale to try to capture some of this stuff.
Yeah, multi-scale hasn't been applied to glaciology in that sense, but I think that, how do you call it, the heterogeneous multi-scale method? I think that could be used perhaps for some of these applications. But overall, glaciologists are quite happy just working with power laws. I think there is some research into essentially more complicated sliding laws. And at times, even sliding laws like this one that have a rate weakening section have been used in studies to speculate about possible instability, since this is essentially unstable, right? Faster sliding is less friction. Some of these ideas have been used to try to explain phenomena like surging. So it's been observed in certain glaciers that every certain years, there's moments of very, very rapid sliding that essentially collapse part of a glacier. So although people mostly work with simple power laws, more complex power laws are used at times to try to explain certain phenomena. But definitely for large-scale modeling of ice sheets, people just stick to simpler power laws. Essentially.
So since essentially this issues with U.N, and I understand you want to have continuous velocity, but are there any approaches in this community to use HT spaces for the velocity? U.N is a natural thing.
Yeah, exactly. No, that's such a good question. Yeah, that was my first go-to as well when I started running into these problems, to just use like a low-order Raviat-Thomas, because then the correspondence between U.N and the average is just natural. Mm-hmm. I think the problem that I encountered was that essentially you have to start using penalization of the discontinuities that arise. And what I observed was that in practice, when I was computing these curves, it did work, but it's actually very inaccurate unless I thought was
the Raviat-Thomas. You have to be.
But I found that the penalization parameter mattered a lot, and it was just very annoying trying to also find the right penalization parameter. So
you'd have to use a different pressure space then, because you couldn't use this pressure space. You can't use piecewise constants with the...
No, I know. I think I did it correctly. I was aware of compatibility conditions and the theory, and I used a different pressure space. I can't even remember which one I used. I guess if I use RT1, it's DG0 pressure, right? That's like the natural Durham complex setting. But my main issue really wasn't about essentially the pressure space. My main issue really had to do with the fact that the penalization parameters essentially really felt like a very narrow range of values that has Stokes. Yeah. Essentially.
But if you use a different pressure space, you can use multipliers because it's in soup stable. So you wouldn't use penalties, right?
What do you mean? I use penalizations for the lack of differentiability of the Raviat-Thomas space. It's not in H1. So
yeah. You're talking about the volume part.
Yeah. The kind of like DG aspect of it.
Yeah.
I found that to be actually very impractical, and it just turned out to be much easier to just work with Taylor Hood in that sense. Essentially. Yeah.
You can still use nodal pressures. It's just they're with the like if you use quads, you could still use nodal pressures. In fact, you could even use it with TETs, but then you'd have to put a bubble function in there for the triangle. Put a bubble.
Yeah, the bubble function that works all right, but then you return to the same thing. Like my normal velocity is no longer piecewise constant, right? Essentially, it's like natural correspondence between piecewise constant Lagrange multipliers and piecewise constant normal velocities that you get with Raviat-Thomas. Essentially,
Essentially, it's 12. And the other breakthroughs in maybe a bit with physics. There could be also like not just about not just the friction, but there could be also maybe plastic. I don't know, stick big boundary over distance with back. Maybe I don't know. Maybe that's ice somehow stakes within the surface.
Oh yeah.
So maybe that would give you even some negative pressures in like some.
That's a very good point. Yeah.
We should speak about maybe more complicated formulation, but in the end, it brings would be better.
So no, I mean, it would be complicated because then I think one way to do it would be to like include temperature effects and measure whether the temperature is below freezing or above freezing. And that would actually give you another variational inequality because you would have a kind of like two regimes that are like discontinuous, right? Like either it's like not below freezing and it can detach and it's not frozen, or it's freezing and then it's frozen. So that would make things quite complicated. But yeah, you can definitely make this as complicated as you want.